Great. So, yeah, welcome back. Any questions from what we were discussing in the previous session? Okay, I have released one homework. Okay, there are no programming questions as part of that. They're all conceptual questions as well as simple problems that you need to solve. Okay, based on what we have already discussed or what we are going to talk about today, you should be able to answer those questions. Okay, they're just simple questions, so I have given about 8 days to work on that. Okay, and then we will have one more small homework similar to this one on the next module. Okay, so that's the plan for now. Okay. So okay, so let's continue with what we were discussing. Okay, so we were talking about memory management techniques, right? And as part of that, we have looked at some basic concepts, especially regarding dynamic loading, dynamic linking, relocation, and so on. Okay, and we also discussed what swapping is and so on. Right. So we talked about all that, and then we were discussing. We were looking at the problem regarding how do we allocate a part of memory to multiple user processes so that we can efficiently utilize the entire memory space that is available. So, so towards that, one one approach is towards that. Of course, we can we can partition the physical memory and allocate an entire chunk of memory to a particular process, such that all the logical addresses or the entire memory that is required for the particular process can be allocated from that particular physical memory chunk. Okay, or in other words, all the addresses related to a particular process are located in contiguous memory locations in as part of physical memory. Okay, so that's the concept of contiguous allocation, and towards this, we have looked at the static memory partitioning approach, where we have where we pre-partition as part of the system setup. What we do is we pre-partition the entire physical memory into some number of partitions, okay? Some number of partitions of predefined size, which can be where we can have all the partitions to be of exact same size, or we can have all the partitions to be of different sizes depending on the kind of processes that will be executed, that will be running on that particular physical system. Yeah. So if we have if we excuse me. So if we take the first approach, where we have equal size partitions, then we should be able to then we should be able to select any of the free partitions over here to allocate the memory space to a given process as long as it fits. Okay? If the required process if the memory capacity that is requested by a particular process is more than the if it is more than the partition size, then we can use the concept of overlays to swap in and swap out and have only the required part of the process loaded in physical memory at any point in time. Okay, and considering that these swap in and swap out of part of the process address space or the process logical address space, it the swapping process actually is happening during the process execution time or runtime. Naturally, the user will perceive the impact on the performance of the application or the process. Yeah. So that is one of the drawback. Another drawback is with equal size partitions is if we have any small process which does not need the entire space that is allocated, that is that it is that is available as part of a free partition. In spite of that situation, the small process is anyway allocated the entire partition, because we cannot really allocate only a part of each partition, but an entire partition is in fact allocated to any specific process. So in this particular case, a particular process, the small process it is allocated more than the physical memory space than it requires. So so for that reason, it ends up using only part of it, and a part of that allocated memory space is unused by the process, and at the same time it cannot be allocated to any other incoming small process, considering that partition is already allocated to some other process. Okay? So that kind of memory which cannot be used, um, it is referred to as internal fragmentation, or a part of memory that is already allocated to a particular process, but but it will not be but it cannot be used by that particular process, neither it can be allocated to some other process. Okay? So that is referred to as internal fragmentation. Sorry. So that is one of the main drawbacks of equal size partition, and that internal fragmentation, if we have internal fragmentation, then naturally there is one part of memory that is not being utilized, and thereby the overall utilization of the memory, it reduces. Right? And that problem can be alleviated to some extent by creating partitions of unequal sizes, if we already know what kind of or processes of what sizes will be executed on a particular system. Okay? Um, but we cannot really eliminate it entirely, considering the processes can be of any possible sizes, or the memory needs of processes may actually change over a period over their execution time, and whereas the partitions over here uh, uh, are created during the system setup time, or in other words, what we are doing here is referred as the static memory partitioning. Okay? So the partition sizes themselves do not change, whereas the process needs for memory may change over a period of time. Okay? So we cannot entirely eliminate the problem of internal fragmentation with static memory partitioning approaches. So that is the primary drawback with this one. Okay, and we have discussed this one, and we have also seen that the number of partitions that are created, that determines the degree of multiprogramming of a system, or in other words, whatever number of partitions that we create during the system setup time, that specify the maximum number of processes that can be simultaneously active in the system at any point in time. Okay, so a static memory partitioning, it results in static degree of multi-programming as well, or fixed degree of multi-programming. Okay. Okay. So this is exactly what we discussed. Another approach of a degree of memory partitioning, which using which we can overcome some of the problems of or some of the drawbacks of static memory partitioning, is dynamic memory partitioning, where rather than predefining the number of partitions and sizes of partitions, what we can do is we consider the entire memory space that is available for processes um, as a single whole, or a single chunk of memory, and as the processes arrive with specific requests or for requests with specific memory capacity, the particular process is allocated as much memory as that process needs. Okay? As much memory capacity that the process needs, okay? From that particular hole, and the remaining the entire remaining space, memory capacity, will be available as a whole again for any future arriving processes to serve their requests. So which is all good, but with this particular approach, what happens is, as processes complete their execution or swapped out for various reasons, the the memory capacity, the memory space that was allocated to that particular process is again free for allocation and is considered as a separate whole. Okay, and if we have two holes, two adjacent holes, then they can be coalesced, and they can form a single whole, so that any request for a larger memory partition can be served for any future arriving process using that larger whole. Okay? And and it's the job of the operating system again to keep track of which process is loaded into which part of the physical memory, and where do we have all these different holes, so that we can so that we can allocate um, some memory capacity from those holes, okay, for any future process. Okay. So this is the concept of dynamic memory partitioning. Again, if you see here, we are really talking about allocating allocating the entire address space of entire physical address space of a particular process in contiguous memory locations. Okay, so that is one important thing to note here, okay, as part of dynamic memory partitioning again. Okay, do we have any questions here? Okay, so let's now. As I mentioned earlier, with the static memory partitioning, where we have fixed where we have all these fixed partitions of various capacities, we when a particular process arrives in the system and requests for memory allocation, we may need to make a choice among multiple free partitions, which are candidates to which have sufficient capacity to serve the incoming request. And depending on um, um, depending on what size depending on what size partition that we select over here, it leads to some amount of internal fragmentation. So if we can make a more appropriate choice, for example, in this particular case, if a request arrives for, say, 7 megabytes of memory by a particular process, then we have 1, 2, 3, and 4. Then we have 4 candidate partitions in this particular example, using which we can serve that request. Okay? Or in other words, we can place that arriving process of 7 megabytes capacity in any of the bottom 4 partitions. Okay? And based on which partition we select, each of them will leave an internal result in an internal fragmentation of different capacities. For example, for the bottom one, which has 16 megabytes, if we place the process with process of 7 megabytes size in there, it will result in internal fragmentation of 9 megabytes. Similarly, the next to the bottom one, if we place it there, then it has 12 megabytes, so that will result in 3 megabytes of internal fragmentation. Whereas if we place in the third and fourth one from the bottom, then that will result in 1 megabyte of internal fragmentation, or in other words, which is the internal fragmentation is the wasted memory capacity. right? So that will result in lesser amount of wasted memory space. Okay, so here in this particular example, we would prefer to store, we would prefer to allocate the incoming request of incoming request in any of these two 8 MB partitions, and not in the 12 MB or 16 MB partitions. Okay. So here we have made this decision based on the internal fragmentation, okay? And we have as part of that, we try to reduce the amount of wasted memory as much as possible. Okay, so that is one way of decision making. Okay? And similarly, for the dynamic memory partitioning approach as well, considering at some point in time, as the processes arrive and leave the system, it may result in the memory having multiple holes of different sizes. Okay, so again here we have a similar problem, though it is it's a slightly different kind, where we have where we may have one hole between two different processes. Okay. So here again we have a slightly similar problem where we have holes of different sizes. Again, we want to again we may want to we may want to play we may want to allocate one of these holes to the arriving processes, such that um, it may result in smaller number of holes or holes of reasonable capacity, so that they can be used again. So there are various factors here again. So for that reason, in short, for both of these methods, the static memory partitioning approach with varying partition sizes, as well as for the memory partitioning methods, we need some kind of decision making to identify which of these available free partitions or the holes um, uh, can accommodate the arriving request from a particular process. Okay. So, so towards that, we have different approaches, and the first one is best fit approach. Okay. So let's say we have 4 different holes or partitions in this particular in this as you can see here, where we have say region or partition 0, 1, 2, and 3. Okay. So if this is the case, then if we allocate, then what this best fit approach recommends is to select the hole or partition which can result in the least amount of wasted space or least amount of internal fragmentation. Okay. So if we can do this, the amount of space that that is left out as part of the hole or the partition is the least as compared to selecting any of the other partitions. Okay. So that is the best fit approach. Okay. So one thing to note here is considering we are trying to find the hole or partition which best fits the incoming process or the arriving process, we really need to go through all the entire list of free partitions or holes. Okay? So we need to go over all the partitions and holes to identify which of them is free and which of them leads to the least amount of internal fragmentation. Okay? So so that is the one overhead, because we need to really go over all possible all the partitions in memory, okay? For each request. Okay? So that is a big overhead. Okay? Okay. And one approach to reduce the amount of overhead towards that is if there is a way that we can have a sorted list of these holes based on their sizes, then we do not really need to then we do not really need to search the entire list, and instead we can stop at a point where we know that the remaining partitions cannot serve the cannot be are not appropriate candidates. Okay, so that is one optimization that we can have with this particular approach, but again, um, ensuring that we always have a sorted list of holes based on their sizes, that again has some overhead. Okay, um, because because of all these because the operating system keeps allocating and deallocating memory to and from the processes. Okay? So again, for that reason, it is difficult to maintain the sorted list itself. Okay, so this is one approach to identify what is the whole from among the multiple candidates to which the arriving process can be allocated. Okay, and similar to the best fit, we have another approach which is referred as the worst fit. So here the concept is if we, instead of allocating the arriving process to the whole that best fits the arriving process by leaving the smallest amount of memory out of it, what the worst fit approach recommends is select the whole that that is a worst fit for the arriving process. Okay? Or in other words, the one that leaves the maximum amount of memory space after the process is allocated that whole. Okay? If that is the case, then the argument here is whatever remaining hole that we have, that may be big enough for any future requests that may arrive in, and for such process, we should be able to make use of this space that is left out, the hole that is left out here, to allocate um, to serve the request from that particular process. Okay, so that is the argument here, and um, and otherwise this approach is similar to the best fit approach, where we really need to go over the entire list of partitions to see which of them is free, and partitions or the holes, to see which of them is free, as well as which of them results in what amount of what size hole. Okay, to identify what is the to identify the hole which results in the largest sized hole, again after partition, after allocation. Yes, yes. What we are really talking about here is a dynamic allocation, where where the resulting hole can be used to allocate another process. Okay, so both the best fit and worst fit approaches over here, they um, for both of them, we really need to go over the entire list of holes or free partitions. Okay, so that's an overhead with both of these approaches. And one way to remove that kind of overhead is by using the first fit approach, where we start the search for the candidate holes from one side of the memory, and we just search only until the point where we find a hole that is big enough to place the arriving process, okay, to serve the arriving process request. Okay? So that is the concept of first fit. Okay? From empirical evaluation, it has been observed that the first fit approach, performance of the first fit approach is pretty close to the best fit approach, okay? Except that it does not have the kind of overhead to go over the entire memory to identify to check with all possible holes regarding how much regarding what will be the fragmentation. Okay. So first fit is preferred, okay, and its performance is approximately similar to the best fit as per observations. And note that with the first fit approach, as we keep using the first fit approach, there is a higher chance that that most of the uh, that there is a higher chance that we may have to perform the search long enough before we can identify an appropriate hole. Okay, so so one tweak with the to the first fit approach is instead of starting the search always from one end of the memory, what we do is we 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 keep track of where or at what point in memory that the previous allocation has been made, and start the search from that point, and go around in the form of a round robin manner. Okay, so that's a so that is referred as the next fit approach, where we start the search from the point where we stopped during the previous search. Okay. So these are the four different approaches that we have. Okay. And here we just have a quick summary of what we just discussed. Okay. So to understand that better, here we have one example. Okay. So let's say here the grayed out areas are all allocated partitions to different processes, and let's say the white ones are the ones which are free blocks, or free, and they are the holes in this particular case. Okay, so here we have holes of size 8 megabytes, 12, 22, 18, 8, 6, 14, and 36. Okay? So in this particular case, let's see if a process arrives requesting with a request for 16 megabyte block. So if that is the case, now let's see which of these different holes get allocated to the particular process based on each of these different four different approaches that we have discussed. Okay. So let's take a look at the best fit approach. Okay. As I said, the best fit approach, based on the best fit approach, we allocate the hole that results in the smallest fragmentation. So considering the request is for 16 megabytes, the only holes that can satisfy that request are 22 megabytes, 18 megabytes, and 36 megabytes. So we have three possible candidates here, and of them, let's see, the 22 megabyte one will, if we allocate that, it will result in a hole of 6 megabytes, and the 18 megabyte one will result in hole of 2 megabytes, and the last one, it will result in a hole of 20 megabytes. Right? So from these, based on the best fit approach, we allocate the second one, which is the 18 megabyte one, because it is resulting in the least sized hole, okay, which is 2 megabytes. Okay. And similarly, if we follow the worst fit approach, then we would be allocating the bottommost one, the 36 megabyte one, and that will result in a 20 megabyte block, 20 megabyte hole that can be used again for any of the future requests. Okay. And if we follow the first fit approach, then the first one that can fit the arriving process would be 22 megabyte hole, okay? And that will result in 6 megabyte hole again after allocation. Okay? And if we follow the next fit approach, then we should know what is the previously or last allocated block. Okay, so we keep a pointer to the last allocated block, which as we can see here, which is the 14 megabyte one. Okay? And we, based on the next fit approach, what we do is we start the search from this particular point, go to the end, and we continue the search until the end of the memory. And if we do not find any free any free hole of required capacity, then what we do is we start the search all over back from the first hole. Okay, so if we start from this particular point, the next one that we have available, which has sufficient space, is the bottommost one. Okay, the 36 megabyte one. So if we allocate that to this arriving request, we will again have a 20 megabyte hole. Okay, so those are all the different holes that can be selected, and that can be selected, and the resulting holes if we allocate that selected hole to the arriving request. Okay, as we can see here. Okay, do we have any questions here? Okay, so let's okay, so here we have just one other example, which shows what happens as processes arrive as we follow one of these different first fit, best fit, or any of the other approaches. Okay, one of those 4 approaches, as we use one of these 4 approaches to allocate processes, to allocate memory to arriving process from any of these holes, then we will arrive at a scenario something like this. Okay, so let's say to start with, let's say we have operating system loaded on one side of the memory, okay, and it is taking up, let's say, some 8 megabyte space, okay, and that leaves let's say some 56 megabytes of hole, okay, one large hole of that particular size. And let's say at some point we have these processes 1, 2, and 3 arrive into the system, and eventually we are left with only 4 megabytes of free capacity. Okay? So there is only one hole which is of 4 megabytes space size. Okay? And at this point, let's say process P2 is swapped out of the system for various reasons. Okay? And that leaves a hole of size 14 megabytes. Now at this point, if a process P4 arrives, which needs a capacity of 8 megabytes, okay, and if that is the case, then there is only one candidate hole which can serve that request. Okay? So let's say we allocate 8 MB out of that 14 MB, and that leaves us a 6 megabyte hole again. Okay? So at this point in the picture F here, we have 2 holes, 6 megabytes and 4 megabytes. Okay? At this point, let's say process P1 leaves the system, leaving a hole of 20 megabytes. Okay? And at some point in time later, let's say the process P2 is swapped back into the system, and that occupies the 14 megabytes of the 20 megabytes. So at this point, we have 6 megabytes. So we have 3 holes in the system, 6, 6, and 4 megabyte size. Okay. Okay. So so at this particular point, we have 3 processes loaded into memory, as well as we have 3 holes between these processes. Okay? And together among these 3 different holes, we have about 6 plus 6 plus 4, which is 16 megabytes. Okay? So now if we see here, we have together we have 16 megabytes, but then if there is any we have 16 megabytes of free capacity in the free memory capacity, okay, in the system. But if a new process arrives, and if that needs say about 10 megabytes of memory, then we cannot really allocate memory to that process, that arriving process, even though we have sufficient memory in the system. Even though we have sufficient free memory in the system, considering we do not have all that free memory in contiguous memory locations, we cannot really serve that particular request. Okay, so this kind of free memory that is dispersed in the system, which is small enough that it cannot serve an incoming request, that is referred to as external fragmentation. Or in other words, the part of memory that is not allocated to any particular process, and at the same time it is not sufficient enough to serve an incoming process request. Okay, or in other words, this particular memory that we have here, it is again wasted. Okay? So that kind of memory area is referred to as external fragmentation in the system. So this is slightly different from the internal fragmentation that we have discussed in the previous slides. Okay, again, whether it is internal fragmentation or external fragmentation, both of them will lead to wastage of memory, or in other words, we are not utilizing memory in an efficient manner, right? So that is so external fragmentation is a drawback of or is a limitation of dynamic memory partitioning approach. Okay. Okay. So I'll let you work on this particular problem. Okay. So I'll not discuss that. You can think about it. Okay. Okay. So now naturally this is a problem, right? Now internal fragmentation, it may be a little difficult to solve because with static partitioning approaches, we allocate entire partition to the process, right? So for that reason, we may not be able to make use of the memory that is already allocated to a particular process. Okay? Whereas with external fragmentation, we should be able to solve um, in some manner, or in other words, if there is a way that we can combine all these three wholes, 6 plus 6 plus 4, if there is a way we can combine, or in other words, if there is a way that we can move all these different processes together to one end of the memory, then then in other words, we are in fact moving all the wholes together. And if as we know with the dynamic memory partitioning, if we have multiple adjacent wholes, we should be able to simply coalesce or combine them and consider them as a single whole. Okay? So if we can do that in this particular example, that will result in one whole of size 16 megabytes, and we should be able to use that whole to allocate the incoming requests of any size less than or equal to 16 megabytes. Okay? And thereby we should be able to use that memory space. Okay? So this approach of moving the processes together to one together to this approach of moving the processes or to one side, or moving the wholes to other side of the memory, that is referred to as compaction. Okay, so that is one solution to solve the external fragmentation process. So it simply moves the processes to one side of the memory so that all these different processes are placed in adjacent locations, adjacent blocks or contiguous blocks. Okay? And thereby we can have the entire free memory available as part of one single whole, and that can be utilized to serve any future requests. Okay? But as we can see here, the compaction, the process of compaction, it results in a lot of additional overhead, considering each of these processes need the entire address space of each process need to be moved to a different location. Okay? So that is definitely one overhead, and it results in additional overhead on the CPU. Okay, or in other words, it wastes CPU time, because because yeah, because the entire process need to be moved, and all that is not part of the um, process execution. Okay, so that is an overhead with the compaction approach. And so external fragmentation, it can be reduced. The impact of external fragmentation can be reduced by using this compaction approach, but it definitely has some limitations. Again, similar to swapping, the concept of swapping that we have discussed. If we if the uh, if the address binding is if the address binding by a particular process or which of a particular program, if it is not done at execution time, or in other words, if it is done either at compile time or link time, then we cannot move the process at runtime. We cannot really move the process from one location to another location in the memory, right? Or in other words, we cannot implement this compaction approach to that particular process. So it is not possible. That is one limitation to this one. And again, similar to swapping, if there are any pending, if there is any pending IO to the process, then again, if we move the process to a different location, that may result in some problem. Okay? So for that reason, either we ensure that we do not move such process from one location to another location in memory, or one part of memory to another part, or what we do is, instead of having the IO device directly write or access the process memory locations, what we can do is can we can allow the IO device to perform read-write operations only to the operating system buffers, or and at some point in time, when the operating system knows that the process is in some part of the physical memory, then it can perform a second copy from the operating system buffers to the process memory area. Okay? And that leads to a double buffering, because the read-write operations need to be performed twice. Okay? So again, that is an overhead. Okay? So all these aspects these are some limitations or additional factors that we need to consider when we are applying compaction. Okay? And note that we are really talking about, so far we have been talking only about the fragmentation in physical memory, okay, which is pretty fast. Okay? But if we place some of the processes in the persistent store or the disk, okay, as part of swap in and swap out, let's say we are placing the processes on the persistent store or on the disk or on the backing store, okay, and so if that is the case, then as we move as we swap in and swap out all these processes, we will have the exact same fragmentation issues on the backing store or the disk capacity as well. Okay? So over a period of time, even on disk, we will have similar problems where we have different holes or different free capacity at different parts of the disk, and to swap in and swap out a particular process, we may also need to find an appropriate hole to um, to swap in or to place a particular process on the disk. Okay, so even on the backing store, we will arrive at exactly same fragmentation problems, and with respect to the overhead, if we want to apply compaction, it is the applying compaction, applying the procedure of compaction on backing store, it leads to a higher overhead and a larger time delay, considering the disk is or the backing store is several orders of several orders slower as compared to um, as compared to the physical memory accesses. Okay? Okay. So it's a bigger problem, and that is something we may want to note. Okay. So for that reason, application of this compaction approach is not recommended at all times. Do we have any questions here? Okay. One small thing to note here is both the internal and external fragmentation together. They result in they result in about 33% less usage of physical memory. Okay, so it has been observed over a period of time that if we have some if we have let's say some 66% of memory allocated to some to processes, then about 33% or of the physical memory, or about a third of physical memory is usually lost to the internal or external fragmentation. These approaches that we have seen. Okay, so fragmentation is in fact a real problem, and it needs to be addressed. Okay, and one approach to address that problem is compaction, and we have seen that with compaction we have all these different limitations. Okay, do we have any questions here? Okay, so now what we'll do is we will look at another approach where we can solve this problem of external fragmentation, but without the use of compaction. Okay, but before we do that, let's take a look at the small concept here. Okay, so so if we think about a particular program, well, if we think of a particular program, with respect to the process, it sees that the program has or the process has different parts of memory. Right? It has a stack space. It has a heap space. Right? It has a code section, a data section, and so on. Right? And with respect to the user, how from the user's perspective, the particular program has different subroutines, a stack space, and different modules of a particular program. Okay? So the user does not really expect all these individual components to be loaded in contiguous and available in contiguous memory locations. Okay? And at the same time, as part of program execution, there may be a situation where any of these components may the memory requirements of any of these components may also grow over a period of time. For example, the stack may grow, as well as the heap heap segment may also grow for a particular process. Okay? So the different modules, they may grow or shrink over a period, over the execution time of a particular process. Okay? And accordingly, the user would expect that the memory is available and allocated to a particular process as required. Okay? And for that reason, there is no real need for all these for all the components to be located in sequential or contiguous memory locations in the contiguous locations in memory. Okay. Okay. So let's say if we have all these different different components of a particular process, then it is not always required that these all these 4 blocks. For example, we do not really expect that the memory is located in one specific chunk to this particular process as 1, 2, 3, and 4, so that all these 4 modules can be placed in contiguous locations in memory. Instead, what we can do is we should be able to place them in different locations, as we can see here, okay? And that may in fact give them an opportunity to grow as required during the runtime. Okay, and okay, and considering that these allocations are being made by the operating system, the process or the user itself does not really need to be aware of whether these individual components are loaded in contiguous locations or at different locations. Okay. So basically, based on this particular concept, we have one solution that can eliminate external fragmentation. Okay? That is referred as a segmentation approach. Okay? So what we can do is with this particular approach, we should be able to divide the entire program or the process logical address space into some number of segments, and each segment may be of some length. So basically, all these different segments, they may vary in their size. Okay? And what we do is we allocate um, allocate memory to a particular process in terms of its segments, or in other words, to each segment we allocate memory separately. Okay? And considering considering all the logical addresses or the entire process is not being loaded in contiguous memory locations, the addressing with this segmentation approach is slightly different. In other words, we may want to first identify for a given logical address, we may want to identify exactly which in which segment that a particular element is placed, that address is located, as well as in that particular segment, what is the specific offset, or what is the relative location at which that address, that logical address can be accessed. Okay, so the addressing, it consists of 2 separate parts and not a simple relocation as we have seen earlier. Okay. Okay. So in this particular case, we obviously should be able to eliminate the internal fragmentation altogether, as in we are able to allocate only the amount of um, memory capacity as required by each of these different segments, and not more than that. Okay. So in that manner, we completely eliminate internal fragmentation. However, the external fragmentation is not completely eliminated, because we still have the similar problem as we have with the previous dynamic memory partitioning approach. Though the overall scale of the problem is smaller, considering here we are trying to um, allocate memory to individual segments and not to the entire processes. Okay? So in that manner, segmentation approach is to some extent it is similar to dynamic memory partitioning approach. Okay. Now considering each logical address, it has 2 different parts, a segment number and an offset. We need a specific approach to convert these logical addresses to the actual physical address at which to the corresponding physical address in memory. Right? So here we have the corresponding approach. Okay? You may take some time and go over this, but we will take a look at an example to understand it better. Okay, but before we get there, let's take a look at some terms. Okay, as I said, the logical address of a particular location that consists of two factors. One of them is the segment number in which the logical address is located, and the the relative address within that particular segment which we are interested in. And okay, so that is referred as the offset. Okay, and now that we have we have um, we have the uh, entire process address space split into multiple segments, and each segment is loaded in a different part of the physical memory. We want to know exactly where each segment is loaded. Okay, so for that reason, we have so that information is stored as part of the segment table. Okay. Now, segment table is the one which has one entry per segment, and it has information regarding the starting location at which the segment is loaded, as well as the maximum size of uh, the size of the particular segment. Okay. Considering these segments may be of different sizes. Okay. So segment table is the one which will help us in translating these logical addresses, which are represented in the form of segment number plus offset, to a one-dimensional physical address, or a specific address, physical address. Okay. Now we're talking about the segment table itself. So segment table is the one which has information regarding all the segments of a particular process. Okay, so it is a process specific data structure that is maintained by the operating system. Okay, and whenever a process is under execution, its information will be loaded. The information regarding segment table will be loaded in these two registers, the segment table base register and segment table length register. So base register is the one which gives the address of the location in memory where the segment table itself is loaded, and the segment table length register gives the information um, regarding number of segments that the process has. And as part of the segment table, we have one row per, we have one table entry per segment. Okay, so the length register is the one which tells us as to how many segments uh, are there for the given process. Okay. And in addition to that, in addition to just having the base address and the limit per table entry, we should also be able to set the validation bit to specify if a particular segment is in fact loaded in memory or not. Okay. Or in other words, if the corresponding table entry is a valid entry. Okay. And we should also be able to set some additional privileges which are like in this particular manner as read, write, execute, so that um, so that we can allow so that we can allow um, sharing of data to some extent among multiple processes. Okay. So these are some concepts that we need to know with respect to segmentation. Now, if you see here, we have we have we have split the entire logical address space into multiple segments, okay? And we are allocating the physical memory capacity to each of these different segments, and we are tracking information regarding where each segment is loaded. Okay? So for that reason, again, here we have the same storage allocation problem where we still need to uh, identify an appropriate hole where each of these segments can be loaded. Okay? So we still have that particular problem. Okay? So that is one limitation with this segmentation approach that we may want to be aware of. Okay. Yeah, so this picture over here, it gives us an overview regarding the translation of logical addresses to or the mapping of logical addresses to their corresponding physical addresses. Okay? So if you see the logical address that is included as part of the program, that includes the segment number as well as the offset, okay? Which is marked with a D over here. Okay? So the segment number is the one which tells us or which identifies the corresponding entry in the segment table. And from the segment table, we get the information regarding the physical memory location where the particular segment is loaded, and which is given by the base value here. And limit is the one which tells us, which gives us the size of that particular segment. Okay? And we can use that limit information to verify if the logical address or if the offset, which is part of the logical address, if it is a valid one. Okay? And so here we can check if D is less than limit, or in other words, if the offset is referring to the correct address, correct relative address within the segment. Okay, and if it is correct, then we should be able to using the base register as well as the offset, we should be able to compute the actual physical address, corresponding physical address. Otherwise, if the offset is an invalid one, then the operating system would initiate a trap, and it will be handled in an appropriate manner. Okay. So this is so that is the overall approach. And here we have one simple example where, let's say, we have a 16-bit logical address which the program, which the CPU sees, okay, which is included as part of the program. Okay, if that is the case, then let's say the first 4 bits represent the segment number, and the remaining 12 bits are representing the offset within that particular segment. Okay, if that is the case, then here the first from the first 4 bits, we see that it is referring to segment number 1. Okay, so that means we should be able to get the corresponding physical location of this segment from the process segment tables entry number 1 or row 1. So from this, the second part over here gives the base or the starting location, where the where this segment is loaded in physical memory. Okay? And the other part, which is the length in this table entry, that gives us the size of this segment, okay? Or the maximum addresses that are available as part of this segment. Okay? Now, from the 12-bit offset of the logical address, if we compare that with the length part of the second row here as part of the segment table, we can see that the offset, the value of this offset is less than the length here, okay, the length entry. Or in other words, which says that the offset is in fact referring to a valid location, okay? Valid location within the particular segment. Okay? So because it is valid, what we can do is we can simply use this offset. We can add this offset to the base address to arrive at the actual physical address corresponding to this logical address that is given. Okay, okay. So this is one example of the logical to physical address translation with the segmentation approach. Okay, do we have any questions here? Okay, So as I mentioned earlier, with this segmentation approach, we have one limitation that that we we still need to perform. Uh, we still need to identify an appropriate hole where the corresponding individual segments can be loaded. Okay, and that again may to that extent it is similar to the dynamic storage allocation approach. Okay, and from that and we already know that this particular approach, it results in having these it may result in multiple holes of different sizes. Okay? Or in other words, it may result in external fragmentation. Okay? So to avoid that particular approach, what we have here is an approach referred as paging. Okay? So with paging, what we do is with paging approach, what we do is instead of partitioning the logical address space of a process into variable sized segments, what we do is we partition the logical address space of the process into fixed size pages, okay? Fixed size chunks, and each of them is referred to as a page. Okay? And at the same time, what we do is we partition the entire available physical memory into same sized chunks again. Okay? And each chunk is referred to as a frame. Okay? So and at the same time, we also ensure that the page size is exactly page size from the logical address space of a process is exactly the same as the of frame size of each frame, which is part of the physical memory. Okay, so now that the page sizes and frame sizes are exactly the same, this the uh, overall allocation problem, it reduces to simply identifying a free frame to which a particular in which a particular page can be placed. Okay? So we can allocate any of the free frames to any of the pages from the logical address space of a process. Okay? So it becomes a simple mapping problem. Okay, so and if you see here in this particular case, because we can um, simply identify any free frame and allocate it, we do not that do not result in external fragmentation here, considering we are considering we are partitioning the entire physical memory into some number of frames. Okay? So, and any of those frames can be allocated to any of the pages. So, so for that reason, we completely eliminate the external fragmentation with this particular approach. But it may so happen that that a particular process may not fit properly into some number of pages. So for that reason, there there may be a possibility that the last page of a particular process, it may not be completely full. Okay? So that may result in some internal fragmentation, but depending on the page size, um, the amount of memory that is part of the last page, or that is uh, allocated as part of the last page that is being wasted is it may be pretty small. Okay, so there is a small amount of internal fragmentation with the paging approach, and we have completely eliminated the external fragmentation. Okay, so here we have one small example where let's say we have about 15 frames in main memory, and those 15 frames, they can be allocated to arriving processes in this particular manner. Okay, let's say process A arrives and it is allocated um, 4 frames. Okay, and process B has 3 pages which are allocated the frames 4, 5, and 6, and process C is allocated another 4 here, and at some point, let's say process B is swapped out, okay? And that leaves 3 frames free here, okay? and those 3 frames can be allocated to the next arriving process, which is D. Okay? So the process D needs 5 frames, and those 5 frames they are it needs 5 frames. So those so it is allocated the frames 4, 5, and 6, and 11 and 12. As you can see here, the all these different frames, they do not even need to be contiguous, and they can be dispersed anywhere in the memory, the physical memory. Okay, and thereby we are making, if not best, we are making good use of physical memory here. Okay, and as I said, the last frame of the process may or may not be completely full, and for that reason we may have a small internal fragmentation here. So in this particular example, the page C3 or D4 or A3, it may not be completely full, and there we may have a small internal fragmentation there. Okay? But then that is limited. The internal fragmentation, even though it is there, it is limited to the maximum size of the frame. Okay? So at max, only one entire last frame can be wasted to internal fragmentation. Okay, and it is again the job of the operating system to keep track of any free frames which are available for allocation from to serve any of the future requests, and it also keeps track of which frames from the physical memory are allocated to which page of each process that is loaded in memory. Okay, so if you see here, for example, process D, the page 0 of process D is allocated to frame 4, whereas page 3 of process D is allocated to frame 11, and so on. Okay, so again, it's the job of the operating system to keep track of that. And if the corresponding information in the page table or if the page table of a particular process is empty, it means that the process is in fact not loaded in memory. Okay? It is not allocated any frame. Okay, so that is another example. And okay, this is what we have seen. So in this particular case, we have the address translation time, which approach, which is simpler as compared to the previous one. So in this particular case, considering the page size and the frame size as exactly the same, what we need to know is just the page number, and we need to know what frame number is allocated to that particular page of a particular process. Okay? So in this particular case, we have the logical address split into 2 parts. One of them is a page offset, another one is a page number. Okay? So if the page size, so if the page size is 2 power n, which is exactly the same as the frame size, then the remaining bits to the left, they represent the page number. Okay? And that page number, we should be able to refer to that corresponding entry in the page table to get the corresponding frame number for that page number. So in this particular case, let's say again we have a 16-bit logical address where we have a 10-bit offset to the right and 6-bit page number to the left. So from the 6-bit page number, we see that the page number is actually 1. Okay, so if we look at the table entry 1 in the page table, we see that the corresponding physical frame that is allocated to that page is 6. Okay, so that gives us the frame number, and that part's the first part of the that becomes the first part of the physical address, and combining that with the offset, we arrive at the corresponding physical address for that logical address. Okay. Okay, so this is one example. This is exactly what we have just discussed in the previous example. Okay, And as we have seen earlier, all these different pages, they may not be even loaded in consecutive frames, and they can be just placed anywhere, and that information we should be able to get from the page table. Okay? And as I mentioned earlier, there is no external fragmentation in this particular approach, but there may be some internal fragmentation depending on the size of the process and the size of the page or frame. Okay? So in this particular example, we have the process size as this, that results in so many number of full pages, as well as one page which is not completely full, which cannot occupy the entire frame that it is allocated, and thereby this is the amount of internal fragmentation that it arrives at. So in the worst case, this can be just one byte that may result in about 2047 number of bytes, or almost the entire last frame to be wasted. Okay? So in the worst case, the internal fragmentation could be a full frame, almost a full frame. And on average, it would be about half of a frame size that we can expect, which is lost to internal fragmentation per process. Okay, so from this we can say that if we have smaller frame sizes, then the amount of memory that is lost to internal fragmentation can be reduced. Okay, but considering that if we have smaller frame sizes, the overall page table size may be high, maybe large, considering there is one entry that needs to be stored in page table per page frame combination. Okay? So that is one trade-off that we need to consider. Okay? But in general, as we have more and more memory, that is physical memory, that is part of the systems over so many generations, it has been observed that that the page sizes are increasing in general. Okay? Usually we'll have about a small page size like this, like 8 KB or so. But sometimes there are these large pages which are supported for special reasons, which may be of size 2 MB or 4 MB. Where if we have these kind of large pages, then they will be usually made use of. They'll be usually used by applications for some specific purposes. For example, we have these databases which have some special data structures that it wants to maintain. Okay, so the large page sizes that you're seeing here, the 4 MB and so on, they are for some special purposes only. But usually we'll have the page sizes as about 8 KB or so, even in modern operating systems. Okay. So this particular example over here, it gives us a comparison among the 3 different approaches: general partitioning approach, paging, and segmentation. Okay. Okay. Do we have any questions here? Okay, so we'll stop here, and we will start the next topic on Thursday. Okay. Okay. You all have a good day. Thank you.
Thank you.
Thank you.